Hello everyone, this is Anthony, and I'll be discussing superposition, electric field, electric flux, and Gauss's law. This is based off Physics for Scientists and Engineers by Serway and Jewett, the 10th edition, designed for an electromagnetism course, such as AP Physics C. Now, suppose you have an isolated system of a finite number of source charges and one test charge. We'll call our test charge big Q, and for each of our source charges, we'll call Q1, Q2, Q3, and so on. If we want to find the net force on our test charge, we have to go to the principle of superposition to find out how to do that. And what the principle of superposition says is that the interaction between any two charges is completely unaffected by the presence of other charges. What this means is that all we need to do to determine the force on the test charge is compute the force from each individual source charge individually. So first we compute F1 due to Q1, ignoring all the other charges. Then we compute the force F2 due to Q2 alone, and so on. And what this looks like is this sum right here. And then to find the net force, we take the vector sum of all the individual forces, which can be written as such. From Coulomb's law, the net electric force on the test charge big Q is, of course, after factoring out K and Q, Coulomb's constant times the charge on the test charge times the vector sum of each source charge over the square distance from that particular source charge to the test charge. And we define the electric field as the electric force on a charge divided by the magnitude of that charge. And that gives us a new definition of the electric field, which is Coulomb's constant times this big sum that I just explained, which we can write compactly as E equals K times the sum of 1 to N of Q over R squared in the direction of R hat. R hat is from the source charge to the test charge. And if the source charge is negative, it's going to be from the test charge to the source charge. Let's do an example. We have to determine the net electric field at the origin due to the two charges A and B of equal magnitude and distance L from the origin. So to start, we use our principle of superposition, which says all we need to do is sum the individual fields from A and B. So the electric field due to charge A equals K times the magnitude of the charge over the distance squared. And it's going to be directed from the source charge to our point. And our point is the origin, which doesn't necessarily have to have a charge there. And our source is going to be L in the positive y direction. So in this case, the electric field is directed in the negative y direction. So we put negative y hat. And the electric field due to B is equal to K KQ over L squared, but this time it's directed on an angle 30 degrees from the origin. We know it's 30 degrees because if this right here is a isosceles triangle, we know each of these angles is 60 degrees. And if this angle right here is 60 degrees, then this angle has to be 30 degrees because they both add up to 90. So EB is directed 30 degrees from the origin, pointing towards the origin, just like this. So what I'm going to do is I'm going to split EB up into its x and y components. So EBX equals B, that's the magnitude, cosine 30 degrees, and we'll put a minus sign on that because it's directed in the negative x direction. And EBY is the magnitude, EBY is the magnitude of the vector times sine of 30 degrees, and put a minus sign since it's in the negative y direction. So in order to get the vector sum of these two, we add the y components and the x components separately. So for the net electric field, is the net electric field is equal to kq over L squared plus kq over L squared sine of 30 degrees. So the net electric field is equal to kq over L squared plus kq over L squared times the sine of 30 degrees in the negative y direction, plus, or rather minus, kq over L squared cosine of 30 degrees, the negative x direction. And sine of 30 degrees is root 3 over 2. No, I'm sorry. Sine of 30 degrees is 1/2. And cosine of 30 degrees is root 3 over 2. So our final answer is the net electric field is equal to negative 1 plus 1/2 is 3/2. Negative 3/2 kq over L squared L squared y hat minus root 3 over 2 root 3 kq over L squared or 2L squared the x direction. And if we want to simplify further, we could say it's equal to kq over L squared vectored out, or rather negative kq over L squared, 3 halves y hat plus root 3 over 2 x hat. And that's our final answer. So far, I've been talking about discrete charge distributions, which is when each of your source charges are separate from one another and in their own locations. Well, most of the time, you're going to have a continuous charge distribution where you have some sort of material, like an insulator, that is charged throughout the whole volume. And while you can't really just say you have a bunch of discrete charges anymore, so what do? We take a teeny bit of our blob, a teeny bit of volume, and we say, well, this volume is going to have a teeny bit of charge. And we call that charge delta Q. And now all of a sudden our summation expression works again because we have multiple charges, different distances from our point. Different distances from our point. And what we do to change our expression into an integral is we allow delta Q to go to 0, which by the definition of an integral gives the new expression for the electric field to be equal to K, Coulomb's constant, times the integral of dq over r squared, where r is again the distance from our elemental charge to our point. Which may seem weird because you're integrating distance with respect to charge, but when you're evaluating this integral, you're probably going to rewrite r and q as functions of the same variable. The charge differential is going to be rewritten in terms of the density. So we have 3 different types of density. There's volume charge density, which is the charge per unit volume, and has units of coulombs per meters cubed. Surface charge density, defined by the charge per unit area, which has coulombs per meter squared as its units. And linear charge density, which is the amount of charge per unit length. So if you have like a charged rod, now say rho, sigma, and lambda are not uniform, and they're a function of some parameter, whether it's distance, time, whatever. If the charge is non-uniformly distributed over a volume, surface, or line, the small element of charge, dq, in a small volume, area, or length, our dq equals rho of some function times dv, which is our small volume element, or sigma of some function times dA, or lambda of some function times dl. And most of the time, they're going to be a function of some distance from a certain point. Notes on vectors. Most of the time, you're going to know the direction of the unit vector without doing any vector algebra. However, if the problem is not simple and you must solve for the unit vector, the following equations will be helpful. If the locations of Q, big Q, and little q are given as vectors in a coordinate space, the separation vector is given by the vector from the origin to big Q, subtract the vector from the origin to little q. from the triangle rule, that gives us this vector right here in orange from the source charge to the test charge. So that's the separation vector. The unit vector, which is what's used in our integral expression, our hat, is a vector of magnitude 1 that points in the same direction as the separation vector. And to get the unit vector, all you do is divide the separation vector by the magnitude of the separation vector, which in this case is going to be our big Q subtract our little q over the magnitude of the two. And to find the magnitude, you take the square root of the sum of the squares of the xyz components, using this expression here, which is just Pythagoras' theorem. Each vector can be broken up into xyz components. Most of the time it's either going to be x and y. And to sum the vectors, you sum each individual component. Example 2. Calculate the electric field using the integral. Here we have a uniformly charged positive rod of length L. The electric field from each individual segment is going to be directed in the negative x direction because the rod is positive and the electric field points away from positive charges. So in order to begin, we begin by writing our integral expression. K times the integral of dq over r squared, our hat, equals the electric field. Now, step 1 is finding an expression for dq. dq is going to be equal to our uniform linear charge density multiplied by dx, a tiny bit of length. So right here in this little section is dq. That's equal to lambda dx. And r is simply x, because the rod is on the x-axis and our origin begins right here. Now, even though it's a distance a away from the origin, we can fix that by just making our bounds from a to a plus L, this point right here, on our integral. So now we have our integral. We have k times the integral of lambda dx over x squared from a to a plus L, where L is the length of the rod. And this is going to give us the magnitude of the electric field. And we know the direction is just in the negative x direction, which can be written as I hat or x hat. They both mean negative x direction. Now to evaluate this integral, we simply pull out the constant, which is lambda, and we're left with the integral of 1 over x squared dx. To evaluate this, we'll use the inverse power rule, which states that the integral of x to the n dx equals x to the n plus 1 over n plus 1. So we add 1 to our power and then divide by the new power. So in this case, our power is x minus 2. Negative 2 plus 1 is x to the minus 1 divided by negative 1. So now this integral is equal to negative k lambda, or rather we'll leave the negative with the integral, k lambda negative 1 over x evaluated a plus L and A, which equals k lambda times, simply insert A plus L into x. So negative 1 over A plus L, subtract negative, which gives us positive 1 over A. The magnitude of the electric field equals substitute lambda for Q over L, since it's positive. Since it's positive and uniform. Since lambda is uniform, we can substitute as the total charge of the rod, which is Q, over the total length of the rod. So E equals Coulomb's constant times Q over L, parentheses, 1 over A minus 1 over L plus A. And the direction is left slash negative x slash negative I hat. As a final conceptual note, we see that our prediction as a final conceptual note, we see that if A becomes larger, that's the distance between the origin and the start of the rod, the denominator in the fraction grows larger, and E becomes smaller. On the other hand, if A approaches 0, which corresponds to sliding the bar left until its left end is directly at or on the origin, then the electric field tends to infinity. That represents the condition in which the observation point P is at 0 distance from the charge at the end of the rod, so the field becomes infinite. We explore large values of A below. Shit. As a final conceptual note, we see that if A becomes larger, the denominator of the fraction grows larger too, and E tends to 0. And if A becomes smaller, or if it goes to 0, then the electric field tends to infinity, which corresponds to point P being directly on the left end of the rod. What if we suppose the point P is very far away from the rod? What is the nature of the electric field at such a point? Well, if P is very, very far away from the rod, that's the same thing as saying A is much, much larger than L. And the denominator, and in the denominator, we can neglect L and basically just rewrite it as 0. So if A is much, much larger than L, then E is approximately KQ over A squared, which is the same for that of a point charge. So what's this mean? It means that if P is very, very far away from the rod, it's nearly indistinguishable from a point charge source. Electric flux. Flux itself can be thought of the flow of something through an area of space. It's best to imagine a fluid flowing through an imaginary rectangle, and the flux as the amount of fluid moving through the rectangle. The volume flow rate of the fluid through the rectangle is dV dt, where V is the volume of liquid that has passed through the rectangle, in small time dt. We can say that dv dt equals dx dt times the area of the rectangle, since the amount of volume that flows through the rectangle is just the linear distance the fluid has traveled times the area of the rectangle. And therefore we say the flux is the velocity of the fluid times the area of the rectangle. However, if our rectangle is an angle to the fluid flow, as illustrated, then we have to modify our expression. And it turns out the amount of fluid that flows through the rectangle is the same, which makes sense because change in an imaginary surface shouldn't have an effect on real physical phenomena. So what we're actually looking for is the component of area perpendicular to the fluid flow. Or rather, if we're speaking of the area vector, which is perpendicular to the surface that has the area, then we're looking for the component of this vector parallel to the fluid flow, which is just the dot product, A dot V. From here we can define electric flux. An electric flux is defined by phi E, which is this capital letter, equals A dot E, where A is the area vector and E is the electric field vector. The integral definition of flux. We use the word flux to mean the surface integral of the normal component of a vector, which just means we take the dot product to find out how the vectors overlay and then integrate the overlay. The previous equation is true if the velocity or electric field is constant over the entire surface. That's the equation from the last slide. However, most of the time, our problem isn't going to have a neat constant flux or electric field. So we have to focus on a small differential element of flux, which is equal to the electric field vector dot the elemental area element, dA. dA is just going to be a small bit of area times the normal vector to the surface. This is a different type of integration from what you're used to, because instead of integrating over the linear x or y axis, you're integrating over a surface. But conceptually, if you can understand this, you won't have to do any weird math in your new equations. And most of the time, due to symmetry, the electric flux integral simplifies quite nicely. Pitfall Prevention 1 for flux. You'll notice we define the flux of the river water as the rate of change. However, flux is usually not a rate of change. Flux is an amount through an area. We basically froze the water in time, and if you wanted to find the volume of water that passed through the rectangle, you would just multiply our result by a time interval, delta t. Electric fields have no such issue, since there's no actual fluid. The flux represents the relative number of field lines, discussed in the last video, given through a given area. Since the density of field lines is proportional to the strength of the electric field, the flux is also proportional to the field strength at whatever point you're finding the flux at. The more field lines that pass through an area, the more flux that is through that area. Let's do an example. Example 3, flux through a cube. Pause the video for a minute to read. We have a cube at the origin and a constant electric field directed in the positive x direction. The four faces that are parallel to the x-axis contribute nothing to the total flux, hence nothing to the net flux. Because the normals are all perpendicular to the electric field, the dot product is 0. And since the dot product is 0, the integral is 0. So again, that's these four sides parallel to the x-axis, or with the normal perpendicular to the x-axis. this side, this side, this side back here, and the bottom of the cube. So top, bottom, left, and right. However, this side back here and this side back here are going to contribute something to the net flux. So we begin by writing the integrals for these two faces that are actually going to contribute to the flux. Phi e equals the integral of side 1 e dot dA plus the integral over side 2 of e dot dA. For side 1, the angle between the electric field and the normal vector is 180 degrees, because here we have the normal vector pointing in the negative x direction, and here we have the electric field vector, I'll get orange, pointed in the positive x direction. So this angle is 180 degrees. Therefore, we go back down to our integral. We can rewrite our first integral as the integral over side 1 e cosine 100 cosine of 180 degrees times dA, which equals the cosine of 180 is -1, so this equals, and since e is constant over the whole surface, we can pull it out of the integral, so it equals -e times the integral over face 1 dA. And so to conceptually understand a surface integral, all of this is the area of our surface. And in this case, our surface is the first side of the cube. So our integral is equal to A, the area of the side. And that makes our expression. The second integral, which is over side 2, is going to be equal to the surface integral evaluated over side 2 of E cosine, what's our angle? Our new angle between the electric field and the normal vector is 0 degrees, because here's our normal vector and here's our electric field vector. Since they're in the same direction, the angle between them is 0. And cosine of 0 degrees is 1. So this expression is equal to EA. And so to calculate the net flux, we add our two expressions together, which turns out to be 0. Which is actually an important conceptual note, because this tells us that the net flux through a cube or any closed surface that only has an external electric field is always going to be 0. Pitfall prevention 2, total flux versus net flux. The question we just did asked for the net flux, and the net flux is the total number of lines exiting a surface, subtract the number of lines entering the surface. Where this surface is closed and it's like the cube or sphere that we were just talking about. Other questions can ask for the total flux, which is the absolute value of our integral expression. The total flux can be asked for the situation of an open surface, the rectangle we were talking about earlier, or it can also be asked for in situations regarding a closed surface. But this is the number of lines exiting plus the number of lines entering. They can be compared to the regular integral or a net area versus the total area or absolute value of an integral for some function. So that's, if you have the integral, you take the absolute value, it's the total flux. And just the normal integral will give you the net flux. A derivation for Gauss's law. We're going to develop a law for electric flux through closed surfaces. These surfaces are imaginary, meaning they exist in our model for mathematical and conceptual purposes. They are not physical entities that exist in the real world. These surfaces are called Gaussian surfaces, and they can be any 3D geometric shape in space. We already know that flux is proportional to field line density, which is proportional to the charge enclosed by a Gaussian surface. The reason flux is only proportional to the charge inside is because, as demonstrated by our last example, the external field has no contribution to the net flux through a sphere or any closed surface. Here is a non-formal derivation of Gauss's law. In a later video, I'll go through a formal derivation, but this is good for building conceptual knowledge. We already established that the net electric flux through a closed surface is proportional to the charge inside that surface. So we know that our final expression should look something like this, right? Or phi equals some constant. No, that's not Coulomb's constant. Some constant. That's also already taken. Some constant C times Q, which is the charge inside. Since outside charges contribute no net flux, we can only focus on the charge inside to find the total electric field. We begin by writing out our flux expression over here. And we begin by computing the dot product. And at all points on the sphere, the electric field is going to be in the same direction as the area vector. So in this case, our dot product is 0 for every point on the sphere. Also, at every point on the sphere, we know the electric field depends on the distance from the point charge, right? And since, by definition of a sphere, the distance from the edge of the sphere to the center of the sphere is the same at all points on the surface of the sphere, we know the electric field is constant over our integral, and we can pull it out. Now we're just left with the integral evaluated over the closed surface, our sphere, of dA, which is simply the surface area of the sphere. So plugging this in, our expression for an electric field due to a point charge, and the surface area of the sphere, we find that the dependency on distance cancels out, because the electric field falls off with r squared and the area increases with r squared. And hence, the electric flux through any closed surface is always equal to 4 pi k times q, the charge inside. And 4 pi k is equal to 1 over epsilon sub naught. Therefore, Gauss's law, the electric flux through any closed surface, is always equal to the charge inside the surface divided by epsilon sub naught, which has a value of roughly 8.8 times 10 to the minus 12th. This gives us our general expression. First, we just have the regular definition of the electric flux through a closed surface, very important remark, is equal to the charge inside the closed surface divided by epsilon sub naught. And this expression is going to be used to calculate not the flux, usually, but the electric field on the surface of our Gaussian surface. So most of the time, this weird-looking integral that we're not really used to will always simplify to just E times A, like in our sphere example, due to symmetry. Zero flux is not zero field. We know that this is the net flux, which will not always correspond to zero field. Just because the integral is zero doesn't mean the field is zero. It just means that the area vector and the field may be perpendicular to each other over your integral. To wrap up, I'm going to end with some final remarks. Gauss's law will usually simplify to the following expression: EA equals Q enclosed over epsilon sub naught due to symmetry in our integral. And most of the time, you'll be solving for the charge enclosed rather than evaluating that surface integral, which we can do using the following expressions for dq. Typically, you're not going to have any examples where the surface integral does not simplify to EA. It's easy to think because of this that the electric field from Gauss's law accounts only for the charges inside, but keep in mind that the electric field represents the total field from all charges present inside and outside the surface.